MRI. Magnetic resonance imaging uses the spins of hydrogen and magnetic fields to create detailed images of the human body. But how does it do that? This technology works because water, which is abundant in our body, contains hydrogen atoms. These atoms have a remarkable property called spin. Just as mass or electric charge are inherent properties of subatomic particles, so is spin. We understand that mass interacts with a gravitational field and electric charge interacts with an electric field. Meanwhile, spin interacts with the magnetic field. The spins of hydrogen atoms are typically disordered in our body, but when interacting with a magnetic field, they begin to act like tiny magnets, aligning themselves with the field, much like a compass pointing in the direction of the Earth's magnetic field. With this alignment, the phenomenon of precession occurs, akin to the wobbling motion of an unbalanced top. In this case, hydrogen atoms exhibit a specific frequency determined by the Larmor equation, stating that the higher the magnetic field, the faster the precession frequency. Let's explore how this seemingly simple phenomenon is ingeniously utilized in the magnetic resonance imaging machine. We need to understand that there are three applied fields: the main field, B0, which goes from head to toe, the gradient field, which has the same direction as the main field, and the transverse field, B1, responsible for generating pulses perpendicular to the main field axis. Let's start by looking at what happens when applying the main permanent field, B0. In this case, the field is the same at all points in our body, causing the precession speed of all hydrogen atoms to be consistently equal. Next, we add a B1 field perpendicular to the B0 field. This field exploits the resonance phenomenon, which works much like pushing someone with their eyes closed on a swing. Only if there's synchronization between the push and the swing will there be an efficient transmission of energy. The same need for synchronization occurs with the precession frequency, acting like the swing, and the B1 pulse frequency, playing the role of the push. In this case, since all hydrogen atoms share the same precession frequency, if B1 is close to the Larmor frequency, they will all resonate and align with the perpendicular field B1. This phenomenon is interesting but not very useful because we want only a few atoms to resonate. We restart, not only with the addition of the main field B0, but also introducing a second gradient field, weaker at the beginning and stronger at the end. This allows for a variation in the resulting field, causing the precession frequency to change according to the hydrogen atom's position. In our example, atoms in the feet would have a much slower spin than those in the head, and atoms in the body's center would have an intermediate frequency. If we then apply our transverse field B1 again at a frequency close to that of the atoms in the body's center, only they would resonate, as there would be no resonance with atoms near the head or feet. Being able to choose which atoms resonate allows us to create a slice in the image at the desired height. But how do we transform the movement of these selected atoms into an image? For that, we need to understand decays, which come in two types, T1 and T2. T2 decay occurs due to the out-of-phase precession when removing the B1 field. Initially, all hydrogen atoms rotate in unison, but without B1, they gradually lose synchronization over time. We can measure the effect of this defocusing, which varies according to the tissue. In water-rich tissues, this phenomenon is slow, while in fat-rich tissues, it's a bit faster. The time between turning off the B1 field and measurement is called echo time. If the measured value at this moment is high, indicating minimal defocusing, the associated pixel will be bright. Conversely, a low measured value results in a dark spot in the image. It is through this property that we can generate the final image. T1 decay occurs when we remove the B1 field, causing hydrogen alignment to return to that of the main field. By measuring the time it takes for hydrogen atoms to return to the initial position, we can form images. Again, each tissue has its characteristics. In water, the decay effect is slow, while in adipose tissue, it is rapid. The time between turning off B1 and this longitudinal measurement is called repetition time. All right, we've managed to grasp a good portion of how magnetic resonance imaging functions. We've seen how to choose the image slice from head to toe by selecting the resonance frequency. We've also understood that it's through the difference in T1 and T2 decays that we can distinguish between tissues. In the upcoming videos, we'll delve into how this measurement is carried out and how we transform these measurements into an image. So, drop a like and subscribe to the channel for future updates.